Hello and welcome to Open Logic. In this video, we'll look into DRAM basics and operation at the level of a memory cell. DRAM stands for Dynamic Random Access Memory. Let's understand it word by word. Memory is a device which can store information. There are many types of memory devices. For example, magnetic tape, compact disc, hard disk, and RAM, dynamic and static. Random access means a user can access any memory location at any point of time. It is not a very good name because hard disks and compact disks are also random accessible even though they are not called that way. In these examples, only magnetic tape is not random accessible. You have to scroll to the specific location in order to access the information there. Dynamic means there is a need to constantly refresh the data to prevent memory loss. We'll look into this later in the video. Other than that, there are several other terminologies. For example, volatile and non-volatile memory. Volatile means a memory requires power to keep its data. DRAM is a volatile memory. It loses its data once its power is cut off. Hard disk, CD, and magnetic tape can retain the data without power supply. They are therefore non-volatile. DDR stands for double data rate. A clock is used to synchronize data transfer. Many devices use one clock edge to send data. Double data rate means both rising and falling clock edges are used to send or receive data. The circuitry is generally more complicated, but the bandwidth is twice as much. DRAM uses capacitor to store data. A transistor is used as a switch to control access to the capacitor. This generally forms a memory cell, and it can store 1 bit of data. To write to the memory cell, first, we enable the transistor. Second, we put data, logical 0 or logical 1, on the data line, and then charges will flow into or from the capacitor, and finally we disable the transistor, and the charges or voltage of the capacitor is stored. Reading from a DRAM memory cell is more complicated. You may think that we can enable the switch, and the charges will flow into or from the data line, and thus giving the data line its value. In simplicity, it is almost like that, but there is a problem. Can you figure out what it might be? The problem is that reading from this memory cell is destructive. The charges is lost from the capacitor, and therefore you would not be able to read the same data again. In order to retain the data, we need to write the data back after we read. Now this causes another problem. Can you figure it out? Well, writing and reading involves charging and discharging capacitor, which is slow. If reading requires an extra write, it basically doubles the time. That is why another mechanism is introduced. That mechanism is by using a sense amplifier. Now let's look at it step by step. The capacitor holds 1 bit of information. It can be VDD or logical 1, or it can be 0 volt or logical 0. The diagram here shows the case when the capacitor is at logical 1. The description is the same if the capacitor is at logical 0, except that the charges flow the opposite direction. The sense amplifier will pre-charge the data line to half of VDD. Now when the transistor is enabled, charges will flow into the data line, but the capacitor only discharges partially. So the capacitor voltage will drop a little and the data line voltage will rise a little. Now the sense amplifier will detect the change and it will decide if the output data is 0 or 1. It can then derive the value as a read data. It will use the value to restore the voltage at the data line and subsequently to the capacitor. Note that in this case, the capacitor never fully charges or discharges, so the operation time is faster. Now let's say we have written 1 bit of information into this memory cell. There is another problem. Can you guess what it is? The answer is capacitor will generally leak charges. If a data is not being accessed for a long time, not even a read, the information will be lost. If you write the memory cell all the time, well, the cell is up to date. If you read from it, a write is performed anyway. However, if the data is idling for a long time, you need to rewrite the data every once in a while. This process is called a refresh, and it gives the name dynamic to DRAM. This is the summary of the operations of a DRAM cell. Now, if you pay attention, you would agree that DRAM cell operation is troublesome. So why do we bother to use it? Is there other option? Well, there is static RAM, SRAM. In the next video, we look into SRAM and see how it is different from DRAM. In the comparison, we will understand why DRAM still prevails despite its somewhat inconvenient operation. If you like this video and want to see more of them, don't forget to like, share, and subscribe.